In this scenario, we're considering a large pond, or at least larger than room-sized pond, which has 10 million liters. So 10 times 10 to the power of 6 liters in it. Into this pond, we have water containing an undesirable chemical flowing in. So we've got flow in, and this is a slow process. It's 5 million, or 5 times 10 to the 6 liters per year. So a fairly slow process to replace all the water in this pond. Of course, if the water isn't to overflow, the water has to flow out at the same rate. So 5 times 10 to the 6 liters per year is also flowing out. And the other important ingredient in all of this is the concentration of the chemical coming in. This is gamma of T, and gamma of T is given by 2 plus sine of 2T grams per liter. So again, we can see our grams per liter, liters per year kind of scenario occurring again. And what we can measure is the net rate of change of, let's call it Q of T, which is going to equal the grams of contaminant. And that is going to be equal to the rate the contaminants are coming in minus the rate the contaminants are going out. We can use units again to guide our construction here. We're talking about a rate of change of Q. Well, Q is in grams, the natural units of time here are years, all the flow rates are in years, and that would be dq dt. The rate in is also going to be in grams per year, and we can see that as the 5 million, or 5 times 10 to the 6th, times 2 plus sine of 2t. Again, the units here, this is liters per year, and this is grams per liter. And the product there gives us grams per year. All of that is our rate in. And then we can subtract the rate out, which is going to be similar. It's going to be governed first by the 5 times 10 to the 6th. That's how much water is leaving, but we're also interested in how much contaminant is leaving. Well, if we take a look at the units here, we had grams per liter, that was a concentration. And we've seen this earlier, the concentration in the tank, or the concentration in this pond, is going to be given by the amount, Q, which is in grams, divided by the volume, which is 10 times 10 to the 6th liters. That'll give us grams per liter. This is in liters per year. And once again, we have the same units, grams per year, when we're done. So we have our rate out as that combination of terms there. So using those same principles as we've seen in earlier examples, we can easily construct a mathematical model for what the level of contamination is going to be in this particular pond over time. Notice that the concentration of contaminant coming in is changing, so there's some kind of variation, some kind of sign thing happening here. And so there'll be higher levels of contamination sometimes and lower levels at other times. And we're going to see what the knock-on effect is on the pond itself. To determine the amount of chemical in the pond at any time, well, again, that's going to be Q, but what we need then is the solution to the differential equation. What was our differential equation? Well, dq dt was 5 times 10 to the 6th times 2 plus sine of 2t minus 5 times 10 to the 6th times q over 10 times 10 to the 6th. Now, when you have some ugly numbers like these running around, it can be helpful to rescale things. Remember that q here is grams. That is going to be a huge number because we have a very big pond. So what we might want to do is let q, little q, be, we've got 10 to the 6s around, so let's let little q be the thousands of kilograms of contaminant. And how would that work? Well, we take the number of grams and we divide it by 10 to the 6th. That's how many, if you divide by 10 to the 3, that's kilograms. Divide by 10 to the 6th, we're going to have thousands of kilograms. how does that play out in terms of rewriting our equation? Well, this value here would be actually little q if we bottle this together. So we can easily replace that q. We also have the derivative to replace though. So what we can do is just reshuffle this for a second. 10 to the 6 times our numbers of thousands of kilograms is our number of grams of contaminant. And from that, we can take the derivative with respect to time. That derivative, we just have a constant, is going to be a scalar of the derivative of q, little q dt. And so we can replace what we have in our equation, capital Q's derivative, with little q's derivative with a multiplier. And so when we do that, let's do that in red here. We have 10 to the 6 dq dt. That's taking that derivative across. Then equals 5 times 10 to the 6 doesn't change. 2 plus sine of 2t doesn't change. Minus 5 times 10 to the 6th. And here we have 1/10 that is not part of our new q, but we also do have a little q on the end, which is our number of grams divided by 10 to the 6th. And if we do that, we see such nice things canceling. We have 10 to the 6th in every single term. We can just cross that off, and we get an equivalent differential equation, which is 5 times 2 plus sine of 2t minus 5 over 10 q's. And we can tidy that up a little bit further and get 10 plus 5 sine of 2t minus q over 2. And that, while having done nothing to determine the amount of chemical, will, trust me, make the solving a lot easier to work with, rather than having all these nasty large numbers running around. You could certainly solve this and it would be fine, but you'll find that working with smaller numbers as you go makes it much easier to avoid silly mistakes. So we now have a new equation. We're going to solve this now for little q. The first step, because it is linear, is to put it into standard form. And that means putting the derivative on one side. We've got that already. But we're also going to move the other q term to the left-hand side and be left with the non-q's on the right. So we'll have plus a half q, and on the right-hand side, we will have our 10 plus 5 sine of 2t. Next step is to find the integration factor, or integrating factor. T is our variable underlying this, and what we do is we grab the coefficient of our unknown function and put that inside our integral. So it's just a half here, and we integrate with respect to time because that's our independent variable. And when we integrate a half, we get 1/2 t. So that's our integrating factor. We're going to multiply our standard form by our integrating factor. That'll give us something that looks nicer. We'll have e to the 1/2 t times q prime. So I'm multiplying this equation by the exponential. We'll have a half e to the 1/2 t times little q. We'll have 10 e to the 1/2 t plus 5 sine of 2t e to the 1/2 t. And the left-hand side is what's most important here. We recognize that the left-hand side is in fact the derivative of a product. So we can simply rewrite it as the derivative with respect to time of e to the 1/2 t times little q. If we do the product rule and expanded, we get that. That leaves the right-hand side identical to where it was before. And we're ready to go. We're looking for little q, so what we're going to do is integrate both sides. We're going to integrate with respect to time. And again, when we integrate the derivative, that effectively cancels out or inverts each other. The more interesting integral is going to be on the right-hand side, when we integrate this fairly complicated function over here. On the left, though, we end up with e to the half t times q, and that's all. On the right side, one of the integrals is easy, 1/2 t, and we divide that by the multiplier in the exponent as a half. This integral is more complex and requires an integration by parts twice, and in fact involves sort of a circular pattern when you look at that integration by parts twice. I'll include that in the text, but won't go through the details here. It'll be on the next page. The upshot of it is, though, when you do that integration by parts twice, you end up with 2/17 times our exponential and sine, our half t times sine of 2t, and you also end up with 8/17 times the exponential again times cos of 2t. Now that is something we can work with. Notice that we have the q, and we cannot forget plus a constant at the end. So that is a much more complex integral that we faced on the right-hand side. That does happen from time to time, but the process of starting with a linear equation and arriving at q equals is essentially the same, aside from that technical challenge along the way. Now, if we do divide by our e to the 1/2 t on the left-hand side, we're going to end up with 20. E to the 1/2 t goes away, plus 10/17 e to the 1/2 t. Oh, that cancels. So we have a sine of 2t alone. We also have minus 40/17 cos of 2t plus the c, but the c is now going to be multiplied by the exponential, negative exponential of 1/2 t, or t over 2. So that becomes our general solution. With this, we can start to ask some questions about what is going on in the pond that we drew here when we have this concentration varying over time. We now have complete information for what's going on with the amount, which is a surrogate for concentration, inside the pond itself.